Okay.
We're recording.
A lot of these rocks around here. These are pieces of bedding rocks here. These rocks break along the bedding, and the bedding shows beautiful ripple marks in here. These ripple marks, by the way, are current ripples. This probably tidal currents. This rock is almost pure quartz. We'll get to see it a little bit better up there where it's bedrock. And what's called highly mature. That is, all the minerals that are at all unstable have broken down to clay or iron oxides or dissolved away, and the only thing that's left is the quartz. So this was probably a very nice beach sand here. Now, what kind of ripple is this?
You can go up the steps.
Is that a current ripple or is it a wave ripple?
They like farming.
How would you tell? That's what you're trying to think of right now, going back. What did it say about wave and current ripples? Wave ripples have a sharp crest and are equally sloped on either side of the crest, and a rounded base. Current ripples are shaped like this. They have a gentle slope on one side, and then they drop down to a steep slope on the other, and then pick up with a gentle slope again. Here's the steep slope here. Here's the gentle slope there. Water was flowing in this direction. So this gives you the direction of the current. Assuming that this is right side up. Because if you turn it over, it looks exactly the same. Now with this one, this is a loose piece of flagstone. And you can't really tell which way they put it. They may have turned it over. Over there, those rocks are in place, and so that we can tell whether they're upright or turned over. But this is some of the nicest ripple marks I've ever seen. The next time you go to the beach, look down along the shoreline when the tide goes in and out, and you'll see the exact replica of that, except it'll still be loose sand then. This is somewhere we think is somewhere in the order of 500 million years old, 500 million plus. Isn't anyone going to ask, how do you know that? Actually, in this particular case, we're somewhat in the situation of the Boston Basin, in that there are nearby rocks that do have fossils in them where you can date it. Just across the valley, on the other side of the Frederick Valley, is the Blue Ridge, and it has rocks that look very much like this. We will get to see them on one of the stops we're going to make, maybe a couple of stops away, and we'll see it. And they do have things like trilobites in them, and we can get a good date on it. Unfortunately, there is no direct connection between the rocks here and the rocks there. As a matter of fact, there are several faults in between, and each of these faults may move things 10 or more miles. Probably the distance between Cumberland and Silver Spring may be 50 miles less than it originally was, because of all the faults that have pushed things over on top of one another. And as the geologists learned in the Boston Basin, the fact that you find two rocks close to each other that look very, very similar does not prove that they are the same. And until somebody finds a fossil in these rocks, then it's still going to be an educated guess. Now, it turns out pure quartz sandstones generally aren't very good for finding fossils. You might. A better bet would be the Urbana Formation, which lies directly over this. See, we are now on the crest of the anticline here, and the Urbana Formation was over this way, which is deposited physically on top of the Sugarloaf Mountain Formation. There is no sharp line between them, by the way. The Urbana Formation is mostly fine-grained sediment, siltstone, fine sandstone, and impure limestone for the protolith. and you get more and more sandstone and more pure quartz layers as you go down towards the Sugarloaf Mountain Formation. And so it's a continuous series of sediments. Conditions just change. Actually, what the conditions were changing were, this was when the ocean first moved in over the underlying bedrock, and the overlying rocks are deeper water. So this is the beach right here, and the rocks on top of it, Urbana Formation, are the deeper water as the ocean moved inland. In some places, you can find this rock resting directly on the Precambrian gneisses. The place where we will get to see it, there's actually a very thick sequence. And there may actually be a fairly thick sequence here because we do not get to see the gneiss here. And I don't know that anyone has drilled to find how far down you would have to go. Anyway, let's go over there to that rock that those people are standing on. A really expensive laptop has all kinds of bells and whistles. The Digistars.
There's another side.
That's right. Okay, this is a good sample of the Sugarloaf Mountain quartzite here. These horizontal fractures are actually the beds. This is very, very thick bedded sandstone. But it also does have a cleavage to it. There is a foliation running approximately in this direction and tilted slightly to the northwest. So it's dipping down to the southeast. There aren't any sheet silicates in this rock. So the existence of that foliation, if you don't think about it, if you do try to think about it, is a little bit of a puzzle. What happens here is that if you get a crack developing and it's perpendicular to the stress, if you put a mineral or any material under pressure, it becomes thermodynamically favorable to dissolve that rock and that mineral and redeposit it somewhere where the pressure isn't quite as bad. And that's what's happened here. It's called a pressure cleavage, pressure solution and pressure cleavage. And it does give you the axial plane of the anticline here. So by measuring the dip on this, which is very, very steep, it's almost vertical, I can then figure out what the orientation of the anticline is, without having to go look on either side. Let's go up to the top and take a look out over the Frederick Valley.
You can climb up if you want, but the steps are a lot easier.
Yeah.
If you're going to the top, this is short. That's shorter. This is quicker.
That way is safer.
Yes.
I got a better opportunity of keeping it.
Okay. This is more comfortable.
Anyway, they claim we're going to have classes in there by January of 2022. And also the city.
Where are you going, Casey? All right, don't go too far. These guys are ready to go soon. You got to think about plans already.
Matter of fact, I'm going to go a little bit because it's related to geology.
It is, yeah.
Okay, this is the Frederick Valley in front of us, which is composite in a way. Part of the Frederick Valley is low-grade marble or slightly metamorphosed limestone. And of course, as such, that means it is soluble. Limestone valleys, limestone does tend to be in valleys in humid climates. In a dry climate, it's a little bit different. But it's also fairly soft, so it does not stand up ordinarily as ridges. Also, the part of the Frederick Valley is a graben. That is, it's a rift valley. We'll get to see that a little bit better at a stop a little bit further down. But the rift valleys here date back to about 180 million years ago, when Pangaea was starting to break apart. It doesn't break apart just along one line. If you stretch the crust, it starts developing cracks all across the area where it's been stretched. One of those cracks is still stretching today. It's called the Mid-Atlantic Ridge. That's the whole Atlantic is sort of one gigantic rift valley. This one stopped after, I don't know, maybe a million years or so, just a short time. In it was deposited a series of red sandstones, conglomerates, some shales, some lake beds, also some volcanic rocks, basalts. We won't get to see those on this trip. We do get to see it on one of the other trips I take. These rift valleys run all the way from Nova Scotia, the Bay of Fundy, between Nova Scotia on one side and Maine and New Brunswick on the other, is basically one gigantic rift valley that's been flooded. Gettysburg is in a rift valley. As a matter of fact, the rift valley here is really the south end of the Gettysburg Basin. The Newark Basin is part of the same rift valleys. They're down in the Carolinas. The southernmost one I know of is in Florida, except that you can't see it because it's been buried under a couple of thousand feet of limestone. But there is a rift valley there as well. That, by the way, I advertise this as demonstrating part of the reason for the breakup of Pangaea. The Rift Valley is the evidence for the breakup of Pangaea, and it comes in the middle of the Mesozoic. On the coastal plain, the late Mesozoic rocks are the ones that are draped over the edge of the continent. So the timing works out beautifully. The early and middle Mesozoic rocks here are deposited in the Rift Valley before the continent has really broken apart. A little bit later, you've got the ocean there, and then the sediments get draped over it from the late Mesozoic on until the present day. How about the evidence for the formation of Pangaea from the collision? Can anyone think of what evidence there is for there having been a collision here? Evidence that we have actually seen today. And I didn't talk about it when we were actually looking at it. We're sitting on top of it right here. Fold. We're sitting on top of a big fold. And that fold is because of the collision. The rocks here have been pushed westward and folded as it happened. As a matter of fact, here it's a little bit more complicated. I've talked about the Martic line, which is the early Paleozoic, when that offshore volcanic island arc was shoved onto North America. And at that time, the rocks were pushed almost on a level plane westward. And so the Martic line started out as a very low dipping, almost like a bedding plane, with flat-lying rocks above and below. You can find the same thing in other more recent faults. Now, that was at the beginning, though. That was maybe 450 million years ago, thereabouts. Since then, Africa hit, and everything was shoved westward and folded when Africa hit, including the fault itself. So if you look at the present orientation of the fault, it's not a flat surface at all. Instead, it's been folded into a hairpin shape, which is fun because the original motion was northwestward in the early Paleozoic. Once it was folded, that part that was folded over, if you're shoving from the east, is in the wrong direction. The motion was back this way, it reversed. And so you had reversed motion on that part of the Marduk Line fault, which is found, by the way, down the hill here, towards the valley. You can actually trace the Marduk Line fault down there, and there's the Marduk Line fault over there near the slate quarry. That's because it's on the other side of the anticline. That is only 2 deformations, by the way. There are places where you find 4 or 5 deformations to a much higher grade. Both of these deformations were quite a ways away from where the actual collision occurred, so that's not messed up too badly. If you take all of this and then metamorphose to granulite facies, where you're almost melting the stuff, oh God, figuring out what happened then, good luck. Okay, looking west here, that is the Blue Ridge on the other side there, and it is indeed an even more gigantic anticline. That particular anticline is several tens of miles across. Sometimes it's given a special name of an anticlinorium, and that basically just translates to really big anticline with little anticlines along the way. And you get similar rocks on both sides in the valleys. In the Hagerstown, in the Frederick Valley here, we will see just a little bit of limestone at our next stop. We don't get to see much of it. I'll get to use my rock hammer there to actually dig down so we can get to see it. And it does have fossils in it, quite a few fossils. And using that, we can then correlate, quote unquote, that's a new word for you, correlate that limestone with the equivalent limestone over on the other side of the mountain in the Hagerstown Valley, because they have the same fossils in them. Correlation sometimes is easy if you've got the right fossils, if you've got lots of fossils. Correlation is not so easy if you've got a fossil-free sandstone, such as the Sugarloaf Mountain quartzite here, and the equivalent, we think, quartzite over in the Blue Ridge. If we had the fossils here, we could pretty well say for sure which sandstone over there correlates with this one. But we can't. We just don't have the information. Okay, now a little bit about I mentioned this other fellow here who has his botany class here, that there is a relation between the botany and the geology. Most of the trees here, many of them, are oak, chestnut oak in particular, which has leaves very much like a chestnut, and pine trees. Oak and pine are very characteristic of dry, rocky soil without much in the way of nutrients. They're adapted to deal with that. Things like beech and maple require more calcium and better soil. And so the soil here is an indication of what the geology is underneath. Now, I did some geologic mapping in Honduras, and it's very difficult in lots of places to get to see any rock at all. You've got deep weathering, and all you can see is the plants. But which plants do you get? It's just on the line between jungle type vegetation, tropical deciduous forest, tropical evergreen forest, with the monkeys and the parrots and such. Rainforest, yeah, and pine forest that looks a lot like Eastern Shore or the Jersey Pine Barrens or someplace like that, because some of Honduras is underlain by limestone, and that gives you the tropical rainforest vegetation, and some of it is underlain by volcanic tuff, rhyolite tuff, which has lots of potassium in it, but almost no calcium whatsoever. Bowen reaction series, calcium comes in at the top and potassium at the bottom. So it's got the potassium, but not the calcium, and it's very silica rich. And that's where you get the pine forest. And you can actually map the underlying rock looking at the plants. That actually has been used in prospecting. When uranium, looking for uranium was big when they were building nuclear reactors and bombs and such. They were very interested in finding uranium deposits. It turns out uranium and the element selenium often travel together, deposited in the same place. And there are some plants that concentrate selenium. Local weed. You might have heard, I don't know if you've ever heard of local weed. Cattlemen do not like it because when the cattle graze on it, the selenium poisons them.
Oh.
It turns out that looking for those plants, though, is a guide to uranium deposits. And so it turns out that the botany becomes very useful in trying to understand the underlying geology where you cannot even see the rocks. In New Caledonia, there's actually a tree that's adapted to serpentine barrens. I've mentioned serpentine barrens before, which are very, very low in almost all nutrients. It has no calcium, no phosphorus, and no potassium. And if you know anything about fertilizer, those are the three things that you put in fertilizer. And it turns out that there are some plants that are not very good competitors. They get crowded out by just about anything else. They're not good fighters, but they're very tolerant of very poor soil. And they are adapted to serpentine barrens. It's even worse than that, though, for the plants that grow in the serpentine barrens, because the serpentine rocks often are rich in chromium or nickel. Chromium, the biggest world supplier of chromium in the early 19th century was Baltimore County. And that's because of the serpentine barrens there. In New Caledonia, there's one tree there that has adapted to the high nickel content there. Their nickel mine is part of the economy of New Caledonia. Nickel mines, one of the main sources of nickel in the world. And there is a tree there that has blue-green sap. You make a slice in the trunk, the sap will come out blue, a nice teal color, I guess you could call it. Aqua, teal, blue-green. And that's because the tree has developed a biochemical way of trapping the nickel in a compound that keeps it from poisoning the tree. So that's its adaptation. And if you could, I haven't seen this yet, but it might be conceivable that you could plant a plantation of these trees on nickel-bearing soil and tap the sap like maple syrup and get your mining done very cheaply by the tree. Probably not practical, because I suspect someone has already thought of this idea, and I have never heard of it being put into practice. But it is something to at least think of. Okay, any questions on here? Going over what I've gone over. First, there's the large scale structures that I've talked about here, the faults and the folds, and the evidence for each. The evidence for the folds is the fact that you can actually see the dip of the bed changing, and you can actually see the axial plane cleavage, both in the phyllite down below and in the pressure solution cleavage up here. And although we don't have time to do it here, you can actually trace the rocks all the way up from our last stop to this one and see the gradual change from the rock equivalent of the Urbana Formation to the rock here that's called Sugarloaf Mountain Quartzite. As I say, it's not an abrupt change. It is a gradual change. I've never done this myself. I'm taking this from what I've read about people that have actually done the geology here. The other one is the study of the rocks themselves and what they tell you. This is beach rock, very shallow water. You've got the current ripples here, and wave ripples also. You find those kinds of ripples here. And the composition of the rock was almost pure quartz rock, compared to the composition of the rock down below, which was rich in clay minerals. that's what gives you the phyllite, but with limestone interbeds, and that's what I should have brought my glass bottle for. But you've seen it fizz before, so you know what it looks like. Then, in addition, I put that in a large scale context, the actual collisions that have taken place here that brought about these rocks. And one of the things about geology is that you have these very, very small scale things that you can look at even under the microscope versus the stuff that you look at on a map of a whole continent. It spans the range of scales. Okay, it's now 11 o'clock. I think the ice cream place opens in half an hour, and we've got to stop to hit before then. So let's head on down.
Do they have chocolate chip cookies out?